Hello everyone, my name is Anton Zaichenko. During the last 10 years, I've been actively involved with Bayesian engineering in developing the earthquake early warning system in southwest British Columbia, and in particular in the Metro Vancouver area. Today, I will talk about approximate inference of the earthquake early warning event parameters using Markov chain Monte Carlo and Bayesian networks. My presentation is structured as follows. First, I will revisit uncertainty in the event parameters using the traditional method. Next, I will introduce Bayesian networks in the earthquake early warning context, and approach exact and approximate inference using Bayesian networks. Afterwards, I will provide an application of the MCMC method and discuss the performance of the MCMC Bayesian network solution using a simulated model. Next, the performance of the MCMC Bayesian network solution using 2015 magnitude 4.8 earthquake in BC will be analyzed. And finally, the presentation will be concluded by looking at the directions of future work. The diagram on this slide depicts the well-known process of estimation of the source parameters from the seismic record in the frequency domain. First, we convert the velocity or acceleration record to displacement. From the displacement spectrum, we identify the horizontal plateau of constant displacement and the corner frequency. Based on the assumptions of material properties, we calculate seismic moment given source coordinates. And finally, compute the rupture plane size using assumptions about the kinematic model. We note that underlying assumptions affect to a large extent the uncertainties in the source parameters. For example, the results may differ even for the most common models of small seismic events by a factor of approximately 2 for a source radius. Since multiple assumptions significantly affect the accuracy of the event parameters in the traditional method, the earthquake early warning solutions are subject to even larger uncertainties. In the seismic risk context, the hazard and vulnerability model parameters are given by two following vectors: eta h, which contains parameters describing the source and propagation path, and eta v, which includes parameters related to the damage model, accounting for both cyclic deformation and peak plastic displacement. The risk model is defined as an exceedance probability of a damage index. It is natural to assume that risk is the largest in the epicentral area, where the earthquake early warning network is sparse. Consequently, it is critical to analyze a joint distribution of the reduced vector of hazard parameters. The question is, why Bayesian networks for earthquake early warning? In earthquake early warning applications, we solve for a subset of hazard parameters, given that information is incomplete, probability of states is partly known, the number of states is finite, dependencies between variables are established in a probabilistic sense, and conditional independence is observed. Bayesian networks match well all these circumstances and provide us with a tool for knowledge representation for reasoning under uncertainty. Consider an example of conditional independence. The statement that variables tau c and pd are conditionally independent given m is equivalent to the joint probability of the distribution of given m being equal to product of the conditional probabilities. The advantage of the Bayesian network is that it decomposes joint probability distribution by introducing sparsity. The joint probability distribution generalizes to the product of conditional probability of children given their parents. Usually, we want to conduct diagnostic inference such that, given evidence, for example, tau c and pd, we want to find the posterior, the conditional probability of m given that tau c and pd. There are three widely used exact inference methods. Brute force, which decomposes a high-dimensional joint probability distribution of variables into the product of conditional probability of children given their parents. Solution is achieved by marginalizing the nodes of interest by performing a summation over entire space. The cost is exponential. Decomposition or deseparation. It is possible when nodes x and y can be separated given Z if X cannot influence Y given Z. There are no active trails. The cost is reduced to the analysis of smaller subnets, but it is still exponential. And finally, the message passing proposed by Kim and Pearl in '83 employ local propagation method for polytrees. Pi messages go from parents and lambda messages go from children. The cost is linear. However, a major limitation of the message passing method is its applicability to polytrees only. Also, all of the exact inference methods are almost impossible to apply to the non-Gaussian variables. The solution is to use approximate inference methods. In this family of methods, Markov chain Monte Carlo MCMC samples from the posterior by constructing a Markov chain. The objective is to sample from a steady-state process. A detailed balance condition, DBC, is satisfied when the probability that flows from edge I to I+1 is equal to probability that flows in the opposite direction. Therefore, there is no net flux of probability along the edge I+1 during the timestamp, which tells us that the chain is in the stationary distribution. Rearranging DBC equation leads to the following form, which further simplifies for a symmetrical proposed distribution, since probabilities G can be cancelled out. Then we look at two possible cases for the right-hand side. Either it is larger or smaller than 0. Examination of the numerator and denominator in the left-hand side term leads us to the ratio of probabilities during the timestamp I. Finally, the acceptance probability of the metropolis algorithm, assuming symmetrical proposal, is minimum of 1, and the ratio of probabilities at the new and the previous steps. Other possible sampling choices are Gibbs sampling, which is similar to taxi cab optimization, Hamiltonian Monte Carlo, or others. More detailed can be found in STAN platform. This slide outlines the algorithm sampling from the posterior using MCMC to compute the event parameters. First, assuming a joint normal distribution for tau C and PD, we set the vector of mean and the covariance matrix. We set the old probability equal to some small number. We initialize M0 and R0, and we initialize the loop parameters, and then we compute the while loop. We sample R and M from the proposed distribution. In our case, these are bivariate normal distributions. We generate acceptance probability following a uniform distribution. We compute tau C and PD from f and h functions, which contain error terms. The functions f and h are highly nonlinear. Then we compute new probability from the bivariate Gaussian, and then if minimum of either one or the ratio of the new versus old probabilities is greater than acceptance probabilities and everything is great, we set the next point in the Markov chain, we set the old probability equal to the new one, and we save points in the solution vector. Here is an example of calculation of the event parameters for a single station. First, we construct a joint distribution of measurements and accept a Bayesian model with children and parents. We construct a stationary Markov chain with distribution matching the measurements. We observe the burn-in period when the chain converges to the steady state. As a result, MCMC samples from the posterior and construct joint probability density of the parameters. This slide provides a similar example, but for 3 stations. In a similar manner, we construct a joint distribution of measurements and use Markov chain to draw samples matching these measurements. Notice a considerable reduction in variance of R, epicentral distance, comparing with a single station case. This is due to a tighter constraint on R from the vector of the arrival times. Performance of the MCMC Bayesian network solution using 2015 magnitude 4.8 earthquake in British Columbia recorded approximately 10 kilometers north of Victoria. The map on the right shows the epicentral area and the seismic stations which recorded the event. The circles indicate the warning time with separation 10 seconds. The plots on the left depict the records in terms of accelerations from the 4 stations closest to the epicenter. The epicentral distances range from 8.2 to 23.5 kilometers, while peak values of S-wave horizontal acceleration range from 3 to 4% of g. As shown in the previous simulated model for 3 stations, observable values of the arrival time place a significant constraint on the parent node represented by epicentral distance. The plots on the left illustrate chi-squared error maps of the epicenter location estimates calculated from 3 and 4 closest stations. One can observe that 95% confidence region is considerably reduced when 4 stations are used. This suggests that the size of the confidence region for the epicenter estimation must be dynamically updated until it becomes less than a predefined threshold. This is particularly important for a case when all near-field stations observe the epicenter from one side only, which is the case with 2015 earthquake. Finally, MCMC will sample from the posterior distributions and construct non-Gaussian distributions of the required event parameters. The charts on the right demonstrate how uncertainties in the P-wave arrival time picking translate into the size of the 95% confidence region for the epicenter. Since running these simulations in real time might be expensive, the picking error can be aggregated into the error term gamma when computing the H function for PD in the MCMC algorithm outlined before. The charts on the left show the joint distribution for the posterior with indication of the final bounds of the confidence intervals. Directions of future work. We want to increase the depth of the Bayesian network and incorporate additional measurement nodes, which are conditionally independent on frequency and peak amplitudes. For example, we want to use measurements based on the envelope of the P wave. Exponential model proposed by Odaka in 2003 works with the envelope of the first 3 seconds of the P wave, and parameters A and B can be calculated with simple least squares. Employ an efficient sampler to reduce computational cost while sampling high dimensions. Employ a realistic regional velocity model while computing the link RT. Investigate more efficient ways to compute frequency represented by tau c by either instantaneous frequency, wavelet transform, short-time Fourier transform, Stockwell transform, or something else. Explore applicability of the low-cost exact message passing method for polytrees and normal distributions. This concludes my presentation. Thank you very much.